Hi everyone, my name is Sibusiso, but you can also call me Coach Sbu. Welcome to the Maths Buddies channel. Here on this channel, I am dedicated to helping you solve maths problems by providing solutions based upon your requests. So whether you're a new viewer or you're a returning one, if you find yourself having a topic that is troubling you, please make sure that you leave that in these videos comment so that I can be able to see that and generate that video onto the next session, right? Now and lastly, just don't forget to subscribe so that you won't miss when you have when I have uploaded the video that you basically requested. So without wasting any further time, we're going to dive straight into today's video. Now here in this video, we're going to be working with question 9 Euclidean geometry. So let's go ahead and go straight into 9.1 question. Now the 9.1 question, they want us to prove this theorem here. So here we're given that O is the center of the circumference, and then we're told that PAT are points that are on the circle, and then now they say we need to prove that POT is twice PAT. Now this is theorem 2, right, in our normal theorems, right, or it is a theorem that belongs in the centers of theorems, right? Now the first thing that you're going to do first is whenever you're writing a proof, you need to write your RTP. So the RTP is basically what they want you to do. So in this case, they want us to show that POT, right, it is 2 times PAT. All right. Then now the next thing is you're going to do a construction. So let's construct, right? So what we're going to construct is we're going to create a line, or we're going to join OA, right, and then extend it. Let's say maybe extend it to, we're going to come up with a letter here. So let me just change the color here. So we're extending it to E, right? So let's say extend to E, right? So what you did here is we joined, right, AO and extended to E. All right, so now from here, this then means now we're gonna let POA then, because now we need to introduce some angles. So POE is going to be O1, right? And then we're gonna say TOE is going to be O2, and then we're gonna also say let PAO to be A1 and TAO to be A2, sorry. All right, now here let's just fill in the information: O1, O2, A1, A2. Now when you created this when we join this AO and extended to E, we created triangle 1 and triangle 2, right? And these two triangles are both isosceles. So what do I say are both isosceles? Because here in this first triangle, PO and OA are radii, and then here in triangle 2, TO and OA are radii, right? So now we're gonna go straight into our proof. So basically what we're going to do into our proof, we're gonna calculate O1 in terms of A1, right? So first of all is when I look in triangle OPA, which is triangle 1 in this case, we see that we're going to say O1, because we need to find what is O1, right? So O1, you can see that it is angle P plus angle A1. So this is basically the exterior of a triangle, and then from here we're going to say, but we can see that P is the same as A1, so those are base angles of a triangle, and therefore O1 is equals to A1 plus A1, which is 2A1. So basically what we did here, we wrote O1 in terms of A1, right? Then we're going to do the same thing in the other triangle. In triangle OTA, we see that O2 is equals to angle T plus A2. So what we just did here, we said O2 is in exterior, same as what we did there, exterior of a triangle. And then here, then we say but T is the same as A2 because base angles of an isosceles triangle. So here forgot to say isosceles triangle. All right, then therefore O2 is equals to A2 plus A2, right? Then it means they are 2A2. So what we just did here, we wrote O1 in terms of A1 and O2 in terms of A2, right? And then now what do we need? We need to understand the whole part, which is what is O1 and O2. So we're gonna say O1 plus O2, right? We know that O1 plus O2 is also known as POT, right? So let me just keep it like that. Now this is equals to, now the value for O1, it is 2A1, and then the value for O2, it is 2A2. Now here we can see there's a common factor, which is 2, and then we're leaving A1 plus A2. Now as you can see, A1 plus A2 is this area, is this part, but when it's combined it gives you PAT, and therefore we're going to conclude then that POT is 2 times PAT, and that is our answer. Alright, so now let's go ahead and look into the next question. Alright, so in the question 9.2, we're going to be applying basically some of the things that we did in the previous proof, right? So because that's how they do it most of the time in your exam. Once you prove something, you're definitely going to apply into the next one, right? So let's read 9.2 here. Now 9.2 reads as follows: AOB and COB are diameters of circle ACDBE with center O. Chords AC, CB, AE, AD, and DE are drawn, and angle D is equals to 50 degrees. All right, now here to answer this question, we'll firstly need to go through the given information and find all the angles that we're given there. Now the method to do to find all the angles that we're given, or to find some of the angles we're given, is the method that is called DRCPT, right? So let me write it here, DRCPT, right? Now DRCPT basically means now that D stands for diameter, right? So it stands for diameter, and then R, that is like radius, and then C, that is cyclic quad, and then P, parallel lines, right? And then T is for tangents. So now basically what we're going to do is we're going to first check if we were given that we have diameters there, right? As you can see here, we were given that we have diameters, right? So this then means now when you're writing the information here, we heard about diameters. So if we heard about diameters, then it means what you're going to write here is a theorem that speaks about diameters. So basically the theorem says if you have an angle subtended by a diameter, and that angle is going to be 90, right? Now in this case, we were given diameters. We were told that AOB, right, and COE, it was supposed to say COE are diameters of a circle, right? Because here we're told that this is the center, right? So this means that AOB is supposed to be a diameter, and COE is supposed to be a diameter, right? Now if AOB is a diameter, this means there is AOB. So let me just do that. If that is a diameter, then it means the angle subtended by that is going to be 90, right? So here we can see that in diameters, C1, plus C2 gives us 90, right? And then what else? When COE is a diameter, this then means that the angle subtended by that diameter will also be equals to 90. So in this case, A1 plus A2 plus A3 is 90. All right, so from here we know that this is angle on semicircle. So both of them angle on semicircle. All right, so now let's go to the next one. The next one here is radius. So do we have radius here? Of course we do have radius. OA, OC, OB, OE are radius, right? So this means here we're going to take out the information that we have about radius. Now when you see the word radius, there are two things that should come into your mind, right? Firstly is the theorem that says angle at center is twice angle at circumference, because that one has a radius in it. Angle at center, right, is twice angle at circumference. And then the second thing is when you have a circle and then you have radiuses, you should look for isosceles triangles. Why? Because if there are two radii equal and then there's one line, there's a chord joining them, that gives you an isosceles, right? So let's first start with the radius here. So here on this side, I'm gonna write the theorem, right? I'm gonna write the theorem, which is theorem 2, right? I'm gonna write the theorem that says angle at center is 2 times angle at circumference, right? So let me go ahead and write all that info about that, right? So the easy way to write it is to first start with the two radius that are given here, angle at center. So I'm going to start with these two here. So let me change that color and make it red. All right, so I'm going to start with these two, right? Now that is O1 because those are the two angles that are at the center. Now what do I see here? So these angles, I can see that is the angle at center, and then now looking at this, I am looking at this angle as being the angle that is at the circumference, like that. Let me use a different color for that. So I'm going to be showing all the angles that are at the circumference, that, right? And then I see also another one, circumference, like that, right? Now these two angles, those are the angles that I see with the center O1, right? So this then means now what I'm going to do here, I'm going to say O1 is twice C1, and then again I'm going to say O1 is twice D. All right, now let's see if I can find another angle. So with this one, I can see there's that, right? So at the right, I can write where there is isosceles triangle D, right? So here I can see there is isosceles in this OA and OE, right? So in OA and OE, and OAE is an isosceles, right? So this then means now that A1 is equals to E1. A1 is equals to E1. So that's base angles, or let me just write it there, base angles of an isosceles triangle. All right, so this is equals to that. So basically also then means now that I also need to take into account that when I'm adding these angles in that triangle, there is going to be equals to, it's going to be equals to 180. All right, now let's go ahead and look into another center. So I can just move around these lines now. So second center, let me look at this one, that is O2, So when I'm looking at O2, that is the angle at center. So moving these away, let me just take these away first, and then I'm going to be bringing them together. If they are multiple, then I'm going to do that. So that is my angle at center. All right, and then now I need to find an angle at the circumference. I see one here. So as long as it touches from E and B, then that's going to be the angle at circumference, right? As you see here, they touch into the circle like that, angle at circumference like that. There we go. So the second one then will be O2 is 2 times A1, and then again O2 is 2 times C2. Alright, now here unfortunately we don't have an isosceles triangle because there's no line joining E to B. Alright, so let's go ahead and look at another circle, another center. First remove these lines. Now I'm moving to this one. Right, see if I have any angle at circumference. Alright, I have this angle. So just as long as these angles that are at the circle, it is touching C and also touching at B, that is how we find it as an angle at the circumference. As you can see, like that. That is the only one that does it. So we will then say that O3, which is the angle at center, it is 2 times A2 plus A3. Alright, so okay, let me just write it so that it can be clear. A2 plus A3. Right, now is there an isosceles triangle here? Yes, there is an isosceles triangle, and that isosceles triangle, we see that angle B is equals to C2, which then also means now that I will also need to consider adding those angles into 180 to find B or C2. Alright, let's move on to the next one. And the next one is going to be O4, right? Now of course O4, that's the angle at center, so of course that's the angle at circumference there, and I also see another one which is there and there. Alright, now what do we say here? We say O4 is 2 times E1, and then we say O4 is 2 times B. Alright, now what about the isosceles triangle? The isosceles triangle, you can see there's an isosceles triangle there, so C1 is equals to A2 plus A3. Or, guess it right, you can say we can find this by also doing this, right? Plus O4 equals to 180, like that. Alright, so now we're done with the radius. Alright, so we found all the angles that we were supposed to find based on the radius. So now we're gonna move on and see if we have the next step. Now the next step is C. So C means cyclic quad, right? So in cyclic quad, you can have any structure that is four-sided, right? So in this case, I see that I have this 1, 2, right? It's a quad, right? It's a butterfly. 2, 2 like that, 3, 4. There we go, right? I see that, right? So this means now here we do have cyclic quad, and the one that we see here is the angle on the same segment. So this is theorem 6, or the third theorem in the group of cyclic quads, right? All right, so that is that. Now this one is saying, oh, here we said angle subtended by diameter, or you can say angle on a semicircle. Then now here we're saying angle on same segment. All right, so here I can see that A1 is equals to C2. I can also see that E1 is equals to B. All right, now is there another one? There's another one here, so I can see another one also like that. Let me take this, sorry. There we go. There's also another one there. So in that one, what do we see? We can see C1 is equals to D, right? We can also see that A3 is equals to E2, like that. All right, so let's see if there's anyone that is all for the cyclic quad. And so let's erase that and go to the next part. Now the next part is parallel lines. We don't see any parallel lines. And then it is tangent. We don't see any tangent. So this basically means now that is the only information that we need to answer the questions. Now here we were told that angle D is 50. So this means now whatever that we do in the first question, we need to get our answer by relating it with angle D, right? So let's go ahead and look into the question then. Now the first question now, which is 9.2.1, it says let's find angle O1, right? Now what you're going to do here is you're going to look into your information, right? We know that we're going to mark everywhere where we see O1, right? Because we know that we have a lot of information here. So let's go ahead and mark that. I can see that there's O1 there, like that. So I'm going to mark O1 there, and I'm going to mark O1 there. And is there another O1? That is the only O1. All others are just here on that isosceles triangle. Now here I'm looking for the O1 that has D, because I do have information about D. As you can see here, this is the one that has D. So basically O1 is twice D. All right, and then I'm just going to take that and say O1, it is 2 times angle D. Now don't forget to write the reason. The reason it's angle at center. It is 2 times angle at circumference, right? Now basically this then means that O1 is 2 times 50, which is 100. O1, right? Now I would like to write O1 here so that we can see the information that we already have. So we have 100 there, right? Now in the next question, they're saying let's calculate E1, right? Now what we're going to do is we're going to go back into our information, remove this, remove that. We're going to mark where there is E1, right? Now here we're told there is E1 here, there is E1 here. See, we're writing all the E1s. There is E1 there, okay. With another E1. I see another E1 here, so they're saying A1 is E1, and hence A1 plus E1 plus O1 is 180. Now out of all this E1, right, we need to find the one that is linked with O1, right? As you can see here, this is the only one that is linked with O1. That is when we say A1 plus E1 plus O1 is equals to 180. That is on a isosceles. So now we're going to say here E1 plus A1, right, plus O1, it is equals to 180, right? So this is sum or interior angle of triangle. They add up to 180, and then now here, so the but E1 is the same as A1. Now that is because of base angles, right, of the isosceles triangle. And therefore what we're going to say is we're going to keep E1, and then in A1 we're going to change it as E1, and then we know O1 is 100, then this is equals to 180, then 2E1 is going to be 180 minus 100. 2E1 is 80, divide by 2 both sides, and therefore E1 is going to be equals to 40 degrees. Alright, now let's go ahead and look into the next question. Now in the next question, 9.2.2, it says that prove that AE is parallel to CB. Now whenever you're doing the proofs, right, whenever you're doing a proof, if they want you to prove there's a cyclic quad, if they want you to prove that there's parallel lines, you always need to assume that what they want you to prove is already true, right? Now what do I mean by this? So this is what I mean. So here, let's say the question, right, when we're given the question, let's say AE was given in the instruction that it is parallel to CD, right? Now if AE was parallel to CD, what was going to be your conclusion then, right? So that's very important, because here we want to prove something. So to prove something, you need to assume first that it is true, so that you can see that if it is true, what are the things that you were supposed to do, or what are the things that you were going to do when that was given as true, right? So here AE is parallel to CB. We assuming that it is true, right? So if that is true, then that will mean that here, first things first that I see here is that we will have a core interior, right? So here, what do we see? We see AE being parallel to that, right? Then that will mean that the core interior, this angle plus this angle, gives you what? Gives you 180, right? So if it were parallel, then we're going to say that A1 plus A2 plus A3 plus C1 plus C2, right? This is equals to 180. Now with this, you don't need to go ahead and try even other ways, right? You just need to look for one thing and then ask yourself, with what you just gathered now, do you have necessary means, or do you have necessary angles, or do you have enough angles to actually show that if you take these and add them, they will actually give you 180, right? Now here in this case we do have, right, because we know that previously we said that A1 plus A2 plus A3, it is 90. That was angle in a semicircle. And we also said that C1 plus C2 is 90, right? So this basically means now that here, this whole part, we know that it is 90, and this whole part, it is also 90. So if you can show that it is 90, then it means we can prove that AE is indeed parallel to CD, right? So let's go ahead and do that. So now, first things first, we're going to say A1 plus A2 plus A3 is equals to 90. What is the reason for this? This angle on semicircle, right? And then we're going to continue to say C1 plus C2 is also equals to 90. And then the reason for that, it is also angle on semicircle, right? Now we're going to add these angles, right? So we're going to then say A1 plus A2 plus A3 plus C1 plus C2, which is basically what's given there. Then now we're gonna say the whole part. The whole part, we know it is 90, plus also this whole part, it is 90. Now 90 plus 90, we can see that it is equals to 180. Now do you see here, we didn't say that this is equals to 90. We showed it that when we add the angles, it gives you 180, right? Earlier we didn't show that it is 180. Here this was just our RTP, right? This was just what we are required to prove here, right? But then now this is the process of proving it, right? So this is the process of proving it. Then here, this is the conclusion that we're doing, right? So when you write the conclusion that we're actually getting 180, you don't have to say this plus this is 180. No. We need to show that the first one is 90 and the second one is 90. Both combined give you 180. Then that's when you then conclude that AE is parallel to CB. Now here you will need to have a reason for this. Now earlier, if there were like really lines that were parallel, right, we were gonna say co-interior, right? But then now, because of there weren't lines that were parallel, then this means it's basically the reverse of that. So you can say converse, right, co-interior angles, right? And that is basically how you prove for this type of question. And that is all for today's video. If you like the video, please make sure that you click the like button and then you share it and leave a comment. Tell me what you know there, and also don't forget to give me any topic that you would like me to do so that I can be able to generate that one. And until next time, my friends, stay blessed by the best, and I'll see you on to the next one. Cheers.